Hey guys, today we're going to do Chapter 8, Section 9, which is on binomial probabilities. So we used the binomial expansion in the last section to calculate binomial formulas, basically. Now what we're going to do is we're going to apply those to probabilities by using binomial distributions, basically. So remember when we talked about probability distributions, where our x values were our random variables and our y values were our p of x, or our probabilities of those random variables. We're going to do the same thing, we're just going to do them with binomial experiments specifically. So a binomial experiment has to have all of these four things in order to actually be a binomial experiment. So it has to have a fixed number of trials or repeated situations. For each trial, there are only two possible outcomes, either a success or a failure. So, for example, flipping a coin would be a binomial situation because either I get a heads or a tails. Basically, anything that's 50-50, where you've got two possible outcomes, would be a binomial situation. So, like true-false questions, it's either true or it's false. Okay? Each trial needs to be independent from every other trial, and each trial needs to have the same probability of success. So in other words, I have a probability for success that remains true no matter how many trials that I do. Alright, the binomial probability theorem says that in a binomial experiment with n trials, the probability of success is p in each trial, and the probability of failure is q, which is just 1 minus p. So if I know that the probability of succeeding is p, then it makes sense that the probability of failure would be the complement, which would be 1 minus p. If I want to find the probability of exactly k successes, I can use this formula here, which you'll notice is very, very similar to the binomial theorem, which was in the last section that we did. So we've got n choose k times p to the k times q to the n minus k. Alright, and I'll just kind of show you how that formula can be used here. So during the 1996-1997 basketball season, Mark Price had a free throw percentage of 90.6%. Consider the situation where he shot 5 consecutive free throws. We're going to let x equal the number of free throws made in 5 attempts. We're going to let p of x be the probability of making those free throws. So if I want to complete this table for the probability distribution, the first box I just want the formula, the second box I want the decimal. So my probability of success is 0.906. What that means is that my probability of failure, or my Q, is 1 minus 0.906, which ends up being 0.094. So here for this first one, this is when I make 0 shots. That means that I failed every single time. So I would have 5 failures, which would be 0.094 to the 5th power. Okay. Then for this next one, I have 1 free throw that I made and 4 that I missed. So 1 that I made and 4 that I missed. So the one that I made, I know that was 0.906 to the 1, and then I missed 4, so that's 0.094 to the 4th. And then remember, I have to have that coefficient. So that coefficient is n choose k. So in this case, I have 5 choose 1 because I made 1. Okay? I can do the same thing over here. So this one's going to be 5 choose 2 for my coefficient. And for my problem, I made 2, so that's 0.906 squared, and I missed 3. Okay. And for this one, I can do the same thing. So this one, I made 3, so it's 0.906 to the 3rd, and I missed 2. And I have 5 choose 3. Okay, over here, I made 4, so it's 0.906 to the 4th times 0.094 to the 1. And I have 5 choose 4. And then the last one here, I made all 5. And that's 5 choose 5, which is just 1. Okay? And this one here is just 5 choose 0, which is also just 1. Okay, so now if you plug all those into your calculator and you get decimals, you should get 0.0000734, 0.00035, 0.00682, 0.0657, 0.31665, and 0.6104. Okay, so those are your probabilities here for the probability distribution. Now what we can do is we can actually just graph it. So remember that on your x-axis is going to be your random variable, so we'll start at 0, we'll do 1, 2, 3, 4, 5. Okay, on your y-axis is going to be your probabilities. So I'll do my p of x values. I'm going to go up to about 0.6, so I'll do 0.6 right here, and that means halfway between that is about 0.3. So this first one here is really small, this one's really small, this one's really small. This one is close to 0.1, so it's a little bit bigger. It's almost a third of the way up there. This one's 0.3, so it's halfway up, and this one's about 0.6, so that's all the way up there. Okay, so what is the probability that he makes 0 free throws out of 5? Well, we found that one. It was 0.0000734. Okay, what's the probability that he makes 4 out of 5? We found that one. That was 0.31665. Okay, what's the probability that he makes less than 5? So in other words, he makes 0, 1, 2, 3, or 4. Well, for that one, it might be easier for us to just calculate the complement of him making 5, which would be 1 minus 0.6104. And if I calculate that out, I get 0.3896. So that's the probability that he makes less than 5. Okay, and then what's the probability that he makes at least 4 out of 5? Well, if he's making at least 4 out of 5, that means that he makes 4 or he makes 5. So it'd be 0.31665 plus my 0.6104. If I add those two together, it would be 0.92705. So that would be the probability that he makes at least 5. And that is everything for section 9.